This is partly joint work with Sándor Kovács and Julia Sacca, and building on recent works of actually several authors. In some sense, the main influence was this for me for reading the second paper. Now, this paper has been out for some time, and but it's somewhat sick. So it underwent several operations and is still undergoing some. So, okay, thank you. Yeah. And so to go back to very old history, it was Kollár and Néron. I think they did the work around 1962. It was published around 1964. That they looked at elliptic surfaces without multiple fibers. And they proved that one can construct another surface, the Jacobian surface, which has the same analytic or eta local structure over C. So if you are looking eta locally over C, these two surfaces are the same. But this other surface also has a section, and then that other surface is unique with these properties. And so now there was a lot of work extending it to elliptic threefolds under various conditions. Dolgachev, Gross, Nakayama did the main work. And then I would like to understand what happens with an arbitrary abelian fiber spaces. So for me, a fiber space is a morphism. X and Z are normally reducible algebraic spaces, and it has connected the fibers in the scheme theoretic sense. I call this an abelian fiber space if the general fibers are abelian torsors. So that means I mean, you can think of it as an abelian variety, but without specifying the actual the identity of the group operation. But I think especially if you are over a field that's not algebraically closed, then these are quite different from abelian varieties. Then I say that one fiber space is a twisted form of another if sort of eta locally on Z they are the same. So that means that you look at sufficiently small eta neighborhoods of points of Z, then the two fiber spaces, they are isomorphic over it. Now, I will have some assumptions, and so I start working over C, but eventually a lot of the theorems will work over an arbitrary base scheme, okay? So I assume that upstairs X, it has log terminal singularities, that they can non-nuclear class is numerically pi trivial, and this pi is locally projective in the eta topology on Z. So sort of these three assumptions I view as very easy to achieve, at least in characteristic 0, if we just run the minimal model program. So you start with any abelian fiber space, you write down the resolution and sort of run the minimal model program. Then you end up with something that satisfies the first three assumptions. In fact, it will even have terminal singularities. And so my last assumption is the one that is not automatic and not clear how restrictive, that I would like it to have actually pure relative dimension D for something. If Z is a surface, then it can be achieved. I can contract exceptional divisors. It is less clear how restrictive this is in higher dimensions. Okay, now so the main theorem is that if you start with an abelian fiber space that satisfies these. Okay, but I could see it, so I was, yeah. Huh? Yeah, well, okay, so maybe they are, I don't know, I think looking at blank screens is usually annoying as opposed to entertaining, but that's fine. Okay, so if you start with an abelian fiber space that satisfies these assumptions, so then I would like to say that it has a twist that has a rational section. Now this needs an assumption, and so that I need a cohomology class which has intersection number 1 with the general fiber. So this looks like a reasonable assumption is almost needed. Then the claim is that there is a canonical untwist, this is T sub eta, that is a twist, so eta locally on Z, the two fiber spaces are the same, and this twist has a rational section. And then this twist is unique. So once I fix my eta, then this twist is unique. And moreover, the construction that I give commutes with smooth base changes. Now, there is a refinement of this, so that that's eta, that doesn't have to be exactly in the second cohomology, sorry, in the 2D cohomology of X, but in this, I just look at the RD's push forward of ZX, it's a global section there. And now in this refined form, the existence of this eta is in fact a necessary condition for the existence of this twist if X is smooth. If X is not smooth, then I don't know exactly what are the necessary and sufficient and conditions. Okay, so now let's be sort of a little bit more precise. Before I was saying that the twist will involve arbitrary isomorphism, but in fact I will use just some very special isomorphisms. I call them translation twists. So these are translations on the smooth fibers, and on every fiber they are in the identity component of the automorphism group. Okay, so in some sense this is sort of the smallest relative automorphism group. You should really think of this as the connected component of the relative automorphism scheme, if that exists. I mean, since I don't assume that the map is flat, only that there's pure dimensional, this relative automorphism scheme might not exist or might not be exactly what you think it is, but so you should think of this as just the connected component. Now, there are lots of properties that are preserved by these translation twists. So, for instance, the push forwards of OX and of omega X, and also the push forwards of ZX. But interestingly, the Lurie spectra sequence is not necessarily preserved. I believe it's preserved over Q, but I have an example where it's not preserved over Z. Also, being Calabi-Yau is preserved, and being hyperkähler is also preserved. I am not quite sure that projectivity is okay. It is probably okay. So Julia Sacca explained to me that in the smooth case, at least it's preserved, and her argument probably works in general, but I just haven't had. Yes, it's a total space smooth. Yes, yeah. And so there are lots of things preserved. They are actually very similar. Yes.
So it's not true that they're different.
Yes, indeed, I have an example, and so it's some. Yeah, I think my example is you start with some elliptic family over an Enriquez surface, then there's an example where the Lurie spectral sequence exactly hits that Z-mass 2 torsion, but in the twist, it does not hit. But I think that that's really, it's a torsion question. Okay. Now, so I was already saying that there is this relative automorphism group that we are interested in. So it is sort of essentially the same as the relative Picard group. And so then, at least if we assume that the morphism is flat. You see, before I assumed only that it's equidimensional. But so there is this theorem, I proved with Sándor Kovács, that if I have a flat projective morphism, I am a characteristic 0, I should have said it, and this X has rational singularities, then the connected component of the relative, the Picard scheme is a smooth algebraic group scheme, and it commutes with all base changes. Okay, so I mean, as you sort of hope, this holds that the connected component of the Picard is actually really nice. So so Yoon-Ju Kim, who sort of wrote up in his paper that if you use the theorem in the next slide, which will come plus if you dig through SGA3 plus works of Artin and Renaud, then it just comes together. So the interesting thing is, at least from the proof point of view, is what's on the next slide, that if there is a flat projective morphism, X has rational singularities, and you are in characteristic 0, then the push forwards of OX and the relative omega X and omega X are sort of as nice as you can hope for. So that the push forwards are locally free, and then if you look in the derived category, then they are just decomposing as direct sums. So the Lurie spectral sequence completely degenerates, and then the last one, the push forward of omega X is just omega X tensored with the push forward of the relative omega X over S. Now, of course, the last one is interesting if omega X is not locally free, which I have not assumed that did. So it's sort of interesting to compare this with all their results. There are lots of results that the push forwards of OX and omega X over S are nice. I mean, sort of the first results, they were when S is smooth and the branch locus is simple normal crossing, that has been important and used a lot. It started with works of Fujita, Kawamata, and myself, Nakayama. And then other case that was studied a lot was when all fibers are nice. For instance, they have Dubois singularities. Yeah. And but sort of maybe the unusual feature of the theorem is that we don't assume things about the fibers. So the fibers, they can have very bad singularities. They can be non-reduced. So we don't know what the fibers are. It's only the total space that we assume that it has rational singularities. Okay. Yeah, so now let's try to go back and see sort of how these twists can be achieved. So I start with an example where I sort of more or less understand what's going on, and then after that, I will give the general construction, where I have much less control about what actually happens. And so in this example, I start with the central fiber will be just the 3 coordinate axes in P2. And then essentially, I just take its universal deformation. Okay? Now, so that's A3. Now in it I take just a plane, and so there are two reasons for taking this plane. So the one is that then the total space has dimension 3, and we have a very clear idea what sort of flops are in dimension 3. And then the other is that if you look at this plane, then all the other fibers are irreducible. So that means that all the birational transformations that I do will happen only in the central fiber. If I had the whole A3, then there would be this these lines where the 3 lines deform to a line and a conic, and then I would have to do something to these lines and conics as well. But here the central fiber is the only thing that's irreducible. Now, then I had this cohomology class whose intersection number with the general fiber is 1. So for the central fiber, I get some integers for each line, the intersection number. And then the only thing I know that the sum of these 3 is just 1, okay? So that means they can be negative, positive, I don't know anything to start with. Okay, so now what I do is to just take the transversal 2-disk to Li, and then I write down a divisor that's supposed to be like eta, that will be the d, just the sum of the ei di. So that's a divisor that has the right intersection numbers. And then I just run the MMP for that. Now you may complain that it's not an effective divisor, but it's fine. So at least in this case, things are simple enough that you can do MMP. And in fact, all I do is to do flops in the central fiber. I just take sort of one line with which there are negative intersections, and then I flop it. And then again, the central fiber is 3 lines, and I just repeat it until all the intersections become non-negative. Now they sum to 1, so that means that one of them will be 1 and the others will be 0, okay? And so now then my distinguished section in this new model that I obtained after the flops will be just a transversal disk to that line L1 prime, okay? So on sort of that model, there are these distinguished sections that I choose are completely clear. But the point is that to come back to my original model, I have to undo all these flops. So that means that I get some divisors that are very, very singular along the Li. So they will be actually non-normal and very complicated. So it is very hard to understand them there. But at least after their flops, it's very clear what is happening. So now, so can we do something similar in general? And so let's assume for simplicity that the pi is flat, and I have a germ. So I don't need flatness, but many of the details become easier. And so I have a central fiber, which is just the components Fi multiplicities Mi, and there's a generic fiber Xk. Now, and so then there is this cohomology class eta, which intersects the generic fiber 1. So that means that I will have the sum of Mi Ei equals 1, okay? So then I have these Eis, I have no control over them, I really have sort of no information except that this sum is 1. And now I try to do the same thing as before. I try to represent this by some this cohomology class by some algebraic variety. So I take a general local complete intersection of codimension D through Fi. Now if I localize enough, then then there will be this Wi which intersects the Fi at just one smooth point, okay? And so, now then, of course the problem is that these are not divisors. They have codimension d. So it is sort of not at all clear how to do any minimal model program with them. And so then let's look at the generic fiber. And now there I get a zero cycle of degree mi. Yeah? So if that component of the central fiber Fi appears with multiplicity mi, that means that that this Wi intersects the generic fiber in sort of mi different points. So I get a zero cycle of degree mi. Now, then if I look at the sum of these zero cycles, that's a zero cycle of degree 1 on xk, okay? Now, okay, so here I use that the generic fiber is an abelian torsor. So that means, okay, now if it was an abelian variety, then I could just add points, and then so I can just look at the sum. Now it's a torsor, so I can still add when the degree is in fact 1. So that means if I have a zero cycle of degree 1 and you pretend you can add, then you actually get a point, okay? And so that will be my section in the generic fiber, and then of course I can just take its closure, okay? Now of course with this construction, I really have very little idea what happens along the central fiber. Yeah, I just know that I have this section, and the other problem is that even if this very frequently this Wi, I can think of them as cohomology classes, yeah, and so that means that the sum is sort of reasonably a cohomology class. But then after I do this adding on the generic fiber and taking closure, it's not clear, and then sometimes this closure is in fact not a cohomology class. So it can happen that this section, that the total space is singular, then it can really happen that these rational sections I have, they do, that there's no cohomology class that can reasonably be said to be exactly this. And so that's why the smooth case is actually nicer, because then every algebraic variety has a natural cohomology class, whereas in the singular case I can really end up with something that's not. Okay, now of course there is the problem that I made the choices of these Wi's. So somehow my claim is that miraculously the end result does not depend on the choices of these Wi's. Well, at least up to this translation automorphism. Okay, so not that it does not depend as a section, but any two choices, I in fact get the same thing. Okay, and so that means that the key that for this the key theorem is, and so if we assume that the base is strictly Henselian or complex analytic local, if you like it that way, so then the rational sections that were constructed by the previous process, they form a single orbit under the translation automorphisms. So here I sort of restate what these automorphisms are, that they are translation on the generic fiber, and are in the connected component of the automorphism group of every fiber. Okay, so that's, and in fact, sort of with that, it is actually rigid. So that means that there's a unique automorphism that sends one section into the other. Now, since this automorphism that makes one into the other is unique, it means that gluing is automatic. Yeah. So once I have these sections locally, because automorphism between two sections are unique, I have no gluing problems. It's completely automatic. So the whole theorem, the essential point is to understand what happens locally. Okay, so here's the idea of the proof what happens locally. Well, and so that if I have two such sections, okay, then I know that on the generic fiber, you know, I just have an abelian torsor that has 2 points, okay? And so there's a unique translation that maps one point to the other, okay? Now that means that the unique birational translation, and so that is a translation on the generic fiber and maps one rational section into another section, okay? Now, well, so what can I say about it? Now here I use that the relative canonical class is Nef, okay? And so I believe so far I haven't used it, but here it becomes important, you know, that if you have two surfaces where the canonical class is Nef, then any birational map between them just an isomorphism. A higher dimension is not true, but at least any birational map between them is a small modification. So that means the exceptional sets on both sides, they have codimension too. And now I need to prove that small modifications are rigid in general, okay? Now, then if, you know, I chose this, so the WIs to be some general complete intersections. So if I do something, for instance, I fix some very ample line bundle, and I choose these complete intersections out of sections of them, that means that these WIs, they're parameterized by an irreducible space, okay? So that means that then this birational modification I get, it should not depend on the exact choice of these sections. And then, of course, if I just choose the same section twice, then I get the identity, okay? So once I have rigidity and identity at one point, then it's an isomorphism everywhere, okay? So now the question is, what does it mean that small modifications are rigid? But yes, so first there's a definition of small modifications. I call an open subset large if the complement has codimension 2. And the birational map is a small modification if it's isomorphism, not just on dense open sets, but on large open sets. Okay. Now the basic examples are the three-dimensional flips and flops. So let me show you at least an unexpected, at least to me that was an unexpected example of flop, where I will show you how to flop the fiber of a product. Okay. So to start with an elliptic curve. And then my base space will be just this cone over E, and there is the projection that projects Z to E, so it's not defined at the vertex. And then my threefold will be just E times Z. And then here are, in fact, infinitely many flops of the central fiber of it, that I just map E times Z, so the Z stays the same, and I just add to E a multiple of pi Z. Yeah, so Z is a point on the cone. It corresponds to a point on the elliptic curve. Okay, so for every M, in fact, this gives you a flop of this curve. So so at least I used to think of flops that you can contract the curve and then you put it in some other way. Now this curve cannot be contracted, of course. It's just a fiber of a family, but it still can be flopped. And in fact, this example is log canonical, so it's not that these are things that sort of we would normally look at. Okay, so then what's the statement about the rigidity of small modifications? So okay, I mean maybe it's so I have something like a trivial family X times S. So S is the base, and there's a trivial family X times S. And then I have another family Y to S, which is projective, and it has geometrically normal generic fiber. And there's a small relative modification between them. So just so it's just a small modification, but the maps commute with projection to S. And now I need to assume that sort of either I have a birational map on each fiber, not necessarily small, just a birational map on each fiber, or S has rational singularities. So if S has rational singularities, that's enough. Then I don't need to know what happens in every fiber. And then the claim is that this Y is also in fact just a product, well, not necessarily with X, but with some small modification of X. Yeah, so yeah, that's I think it might come quite handy in other situations. So yeah. Well, as you see, and so the cone over elliptic curve does not have rational singularities. Yeah, yeah. So it's exactly.
So what happened? So you had that other.
And then the map is just not defined on the elliptic curve. So it's exactly there are the fibers. There are the two central fibers, and the exceptional set contains the exceptional fibers. Yeah. I mean, these special fibers, yeah? And so, but this also means that sort of this flop I can do only with that fiber. That the other fibers, they cannot be flopped. But this very special fiber can be flopped. Which is good because then we wouldn't have rigidity. Yeah? If I could flop every fiber, then there would be clearly a deformation there. But here I can flop only that one. Okay. Yes. Actually, I think I'm going fast. Okay. Okay. So which is a bad sign usually. Yeah. Okay. Yeah, so
I can slow you down if you want. This previous thing with the infinitely many plots, this idea there's finitely many minimal models.
well, and so yeah, I think it says that in the log canonical case it's not true that there are only finitely many minimal models. Okay. Now sort of why so okay, you might ask why this has not come up so far, and so the point is that if you do this, then the Cartier divisors on one side are all sent to non-Cartier divisors the other side. Yeah. And so sort of that's why sort of normal MMP, even the low canonical case, does not see that. So normal MMP, they wants to have at least some divisor that's at least Q Cartier on both sides, but here it is destroyed completely. So you know, and so singularity along the central fiber is like cones over elliptic curves. So that means that the local class group has this abelian and component, and so what happens? But yeah. So I think depending on exactly how you formulate what you mean by finiteness of minimal models, this at least shows that in the low canonical case, maybe you should sort of state carefully what you want. Yeah, yeah. Okay. Oh yes. So then, what to do in positive characteristic, or actually over an arbitrary base? So first, what to do with this eta? Yeah. So that was a cohomology class to me. Okay, but if you looked at this outline of the proof, then I just needed some function that assigns to every irreducible component of every fiber an integer, and it has this property that, you know, that if you specialize something, then this integer becomes that it commutes with that. So that means I really don't need that this eta is a cohomology class. I just need that there is a sensible way to associate an integer to every geometric component of every fiber. And then, of course, I need, so if the field is not algebraically closed, then components might be conjugate, and then I need to associate the same number to them, okay? And so, but otherwise, this is all I need about eta. I don't need anything further. Now, then the other thing is, well, so how can I say something in arbitrary characteristic where we don't know minimal models? So in fact, once I have an x to z where x has terminal singularities and kx over z is NF, then MMP is not used further in the proof. Okay, so now of course, I said at the very beginning that these three assumptions about the singularities and kx being NF or relatively trivial, they are very, very easy to satisfy. Well, they are very easy to satisfy in characteristic 0 because MMP works. In characteristic P, of course, we don't know whether MMP works, but if I start with sort of what would be the outcome of the MMP, the rest of the proof does not use MMP, so it works over arbitrary basis. Well, I know, let's say excellent, yeah, maybe a few more. Now, there is one assumption, though, that I really need that every irreducible component of the reduction of a fiber should be geometrically reduced. Okay, so this again in characteristic P. There are these schemes over imperfect field that are reduced but not geometrically reduced. So for instance, means that over spec Z this is not a problem. But yeah. Now, then of course the local freeness of Ri G lower star OX, it can fail even for smooth morphism in characteristic P. So I'm not saying I can do anything, and so that it sort of does not affect the proof of the main theorem, but it becomes sort of less clear what these translation automorphisms are. So it sort of makes it a more mysterious object than normal. Okay, now then the other thing at the end. So in some sense, it's not very closely related to what I have been speaking so far, but so with Julia Saka, we were reading this paper of Bagamola et al. And so there were some parts in it that we tried to understand, sort of how this works. So and so at least so what's here is a counterexample of some implied statements in some version of that paper. Okay, so but it sort of shows that this section, business findings section, might be sort of trickier than maybe at least how we thought first. And so basically what we did is a computation of the sections in sort of one case. The assumptions here are sort of simpler than the general statement, but so this is already sort of this is a nice illustration. So start with a smooth projective surface. Let's assume that this Picard group is generated by a very ample class H, okay? Now then I can look at all the curves in H, and I just look at the universal compactified Jacobian, okay? So we have over the smooth fibers, it is just the Jacobian, and in fact, for the proof, we only need to understand what's happening in the nodal fiber. So the thing is okay, but sort of the proof is needs only the smooth and the nodal fibers. Okay, and then so let's take a general line in H. So it's a pencil. And then I want to look at its pre-image. So yeah, so then I have this is maybe the easiest way to get an abelian fiber space. You start with a family of curves and you look at the universal Jacobian. And then, so here the parameter space, the base space is this projective, this space, and then I just take a general line. And then I want to understand what's the relationship between the sections over a general line and at least the rational sections that exist everywhere. And sort of the conclusion is that sort of these have basically nothing to do with each other. Yeah? So that the self-intersection of H is R, and the genus of the curves in H is just G. Then first thing we computed the Mordell Weil group over the line, and that is Z to R minus 1. So that's of course not surprising. So this pencil has altogether R base points. So to get a morphism, you blow up these base points. So this gives you R sections, and then the claim is not hard to see that sort of these is in fact the whole Mordell Weil group. And now you can also look at, well, whether these are cohomology classes that come from the cohomology class of the total space, yeah? And the conclusion is that only the 0 section comes from a cohomology class of the total space. So for almost all the sections, there's a topological obstruction why it cannot be extended to a rational section. Yeah, so now maybe I would like to end with a question. I hope that somebody actually knows this already. So I start with a smooth projective curve over a field K, and then I have a smooth group scheme over it with irreducible fibers. Okay, so and I don't assume that that this is proper. Yeah, so so that means that that if you think about generally start with something projective, and then you have to sort of throw away some things to get irreducible fibers. But for smooth group schemes, that's a reasonable assumption. And the generic fiber is an abelian variety. Now there is the 0 section. Now, just so that I could state this easier, let's assume there is no trivial abelian factor. Okay, so that the generic fiber has no abelian subvariety that's defined over the ground field. And now, then this assumption guarantees that the Mordell Weil group is finitely generated. Okay, and so now I have this natural map. I just take an element of the Mordell Weil group that's a section, so then I can just map it to the section minus the 0 section. That is a one cycle in A, and then well, sort of is it actually an injective group homomorphism? So with special right-hand side, I look at just numerically. And so maybe injective modulo torsion. I think the torsion is not an issue, but I'm sort of not sure. I haven't thought about this. So now the interesting thing here that on this Mordell Weil group there is a shear Tate height that shows that it's finitely generated and provides a height function in the case when I start with some families of curves, but the papers they really avoid these questions. So what happens in the total space? So if you start with a family of curves, well, that gives you a surface, and the shear Tate height is constructed from the intersection numbers on that surface. At least the papers I have seen, they say nothing how this relates to the intersection numbers on the universal Jacobian. And so I think that I'm okay. Then that's it. So I am 52 seconds early. So.